Energy efficiency in compressors, a medium-level module that will explain the main factors that influence in the energy efficiency in compressors. The main factors that influence in the energy efficiency in compressors are this: location, elevation, air intake, pressure drops in air filter, use inter and after coolers, pressure settings, minimizing leakage, condensate removal, controlled usage, compressor controls, and the last one, maintenance practices. The location of air compressors and the quality of air drawn by the compressors will have a significant influence on the amount of energy consumed. Compressor performance, as a breathing machine, improves with cool, clean, dry air at intake. Altitude has a direct impact on the volumetric efficiency of a compressor. The effect of altitude on volumetric efficiency is given in the table. It is evident that compressors located at higher altitudes consume more power to achieve a particular delivery pressure than those at sea level, as the compression ratio is higher. The effect of intake air on compressor performance should not be underestimated. Intake air that is contaminated or hot can impair compressor performance and result in excess energy and maintenance costs. If moisture, dust, or other contaminants are present in the intake air, these contaminants can build up on the internal components of the compressor. The compressor generates heat due to its continuous operation. This heat gets dissipated to compressor chamber and leads to hot air intake. This results in lower volumetric efficiency and higher power consumption. As a general rule, every 40 C rise in inlet air temperature results in a higher energy consumption by 1% to achieve equivalent output. Hence, cool air intake improves the energy efficiency of a compressor. When an intake air filter is located at the compressor, the ambient temperature should be kept to a minimum to prevent reduction in mass flow. This can be accomplished by locating the inlet pipe outside the room or building. When the intake air filter is located outside the building, and particularly on a roof, ambient considerations may be taken. A compressor intake air filter should be installed in, or have air brought to it from a clean, cool location. The better the filtration at the compressor inlet, the lower the maintenance at the compressor. However, the pressure drop across the intake air filter should be kept to a minimum. The pressure drop across a new inlet filter should not exceed 3 pounds per square inch. As a general rule, for every 250 mm WC pressure drop increase across at the suction path, due to choked filters etc., the compressor power consumption increases by about 2% for the same. Perfect cooling. Ideally, the temperature of the inlet air at each stage of a multi-stage machine should be the same as it was at the first stage. This is referred to as perfect cooling or isothermal compression. But in actual practice, the inlet air temperatures at subsequent stages are higher than the normal levels. Intercoolers. Most multi-stage compressors use intercoolers. These are heat exchangers that remove the heat of compression between the stages of compression. Intercooling affects the overall efficiency of the machine. After coolers. As mechanical energy is applied to a gas for compression, the temperature of the gas increases. After coolers are installed after the final stage of compression to reduce the air temperature. As the air temperature is reduced, water vapor in the air is condensed, separated, collected, and drained from the system. Use of water at lower temperature reduces specific power consumption. However, very low cooling water temperature could result in condensation of moisture in the air, which if not removed would lead to cylinder damage. For the same capacity, a compressor consumes more power at higher pressures. Subsequently, compressors should not be operated above their optimum operating pressures, as this not only wastes energy, but also leads to excessive wear, leading to further energy wastage. The volumetric efficiency of a compressor is also less at higher delivery pressures. Reducing delivery pressure. The possibility of lowering and optimizing the delivery pressure settings should be explored by a careful study of pressure requirements. The operating of a compressed air system gently affects the cost of compressed air. Operating a compressor at 120 psig instead of 100 psig, for instance, requires 10% more energy as well as increasing the leakage rate. Therefore, every effort should be made to reduce the system and compressor pressure to the lowest possible setting. Compressor modulation by optimum pressure settings. Very often in an industry, different types, capacities and makes of compressors are connected to a common distribution network. In such situations, proper selection of a right combination of compressors and optimal modulation of different compressors can conserve energy. For example, where more than one compressor feeds a common header, compressors have to be operated in such a way that the cost of compressed air generation is minimal. Segregating high and low pressure requirements. If the low pressure air requirement is considerable, it is advisable to generate low pressure and high pressure air separately, and feed to the respective sections instead of reducing the pressure through pressure reducing valves, which invariably Pressure drop is a term used to characterize the reduction in air pressure from the compressor discharge to the actual point of use. Pressure drop occurs as the compressed air travels through the treatment and distribution system. A properly designed system should have a pressure loss of much less than 10% of the compressor's discharge pressure, measured from the receiver tank output to the point of use. The longer and smaller diameter the pipe is, the higher the friction loss. Pressure drops are caused by corrosion and the system components themselves are important issues. Excess pressure drop due to inadequate pipe sizing, choked filter elements, improperly sized couplings and hoses represent energy wasted. This table illustrates the energy wastage if the pipes are of smaller diameter. Typical acceptable pressure drop in industrial practices 0.3 bar in the mains header at the farthest point and 0.5 bar in distribution system. Minimizing leakage. Compressed air leakage accounts for a substantial power wastage. The best way to detect leaks is to use an ultrasonic acoustic detector that can recognize the high-frequency hissing sounds associated with air leaks. Leaks occur most often at joints and connections. Stopping leaks can be as simple as tightening a connection or as complex as replacing faulty equipment. Condensate removal. After compressed air leaves the compression chamber, the compressor's aftercooler reduces the discharge air temperature well below the dew point. Therefore, considerable water vapor is condensed. To remove this condensation, most compressors with built-in aftercoolers are furnished with a combination condensate separator. Controlled usage. Since the compressed air system is already available, plant engineers may be tempted to use compressed air to provide air for low-pressure applications such as agitation, pneumatic conveying or combustion air. Using a blower that is designed for lower pressure operation will cost only a fraction of compressed air generation energy and cost. In some companies, staff use compressed air to clean their clothes. Apart from the energy wastage, this is a very dangerous practice. Compressor controls. Air compressors become inefficient when they are operated at significantly below their rated CFM output. To avoid running extra air compressors when they are not needed, a controller can be installed to automatically turn compressors on and off, based on demand. Also, if the pressure of the compressed air system is kept as low as possible, efficiency improves and air leaks are reduced. Good and proper maintenance practices will dramatically improve the performance efficiency of a compressor system. Here are a few tips for efficient operation and maintenance of industrial compressed air systems. Lubrication. Compressor oil pressure should be visually checked daily, and the oil filter changed monthly. Air filters. The inlet air filter can easily become clogged, particularly in dusty environments. Filters should be checked and replaced regularly. Condensate traps. Many systems have condensate traps to gather flush condensate from the system. Manual traps should be periodically opened and reclosed to drain any accumulated fluid, and automatic traps should be checked to verify they are not leaking compressed air. Air dryers. Drying air is energy intensive. For refrigerated dryers, inspect and replace pre-filters regularly, as these dryers often have small internal passages that can become plugged with contaminants. Thanks for watching this video.